Okay, so what we're going to do is look at probably the most popular distribution in statistics, and that is the normal distribution. And since all distributions can basically be whittled down to this so-called standard normal distribution, we're going to learn how to read this curve and how to find probabilities with this curve first before we move on to applications. So the standard normal distribution, which is usually denoted with the letter z, so we call z the standard normal random variable. It has a mean of 0 and a standard deviation of 1. So that means that there's basically a double meaning here, meaning that a value of z equals 1, for example, is 1 standard deviation above the mean. And I don't have to be limited to whole numbers. I could come down here and say, let's say this is z equals negative 1.74. That means that this is 1.74 standard deviations below the mean. So that's going to be very important when we start translating back and forth between applications and the standard normal curve. So to understand how to find probabilities with the normal curve, since this is an example of a continuous distribution, we know that the probability associated with value or values of z is translated by looking at the area under the curve. But the problem is we don't know enough about this curve. In fact, the equation of this curve is somewhat extensive and involves square roots and pi, so oh my. But that is the equation of the curve, and since it's not one of our basic shapes like a circle or an ellipse or whatnot, it would require calculus to find area under the curve. But of course, we can do this without calculus. We can do so by making use of a standard normal chart. So what we start looking at is, let's say we want to find the probability that z is less than or equal to some number a. And I'm just going to draw a general normal curve here. So here's 0, and let's just say that a is over here to the right. It doesn't have to be. So it is translated by this area to the left of a all the way down. And what we have is a standard normal chart right here that tells us what these values are. So the way we read it is we look, accuracy to 2 decimal places for the z-score is considered quite enough. And if we look at this chart, let's just say we want to look at a z-score of, say, 1.74. You notice this is highlighted for you. But here is the row for 1.7, and here is the column for 0.04. So where those two entries meet is the area that corresponds to z equals 1.74. So the area there would be 0.9591. So I'm just going to reset this for the next time we use this. Let's look at a couple examples. So let's say in the first one that we want the probability that z is less than 1.43. So since the table gives us cumulative values up to a z-score, this is right up that table's alley. We're going to go to this table and we're going to look for 1.43. So looking at the 1.4 row and the 0.03 column, it looks like that probability is 0.9236, which means the area under that curve is 0.9236. So I'm just going to write that in here. 9236, there we have it. Now what happens if we want an area to the right? Well, remember, the area under the entire curve is 1. That's a requirement of a probability distribution. So that means that if my table gives me the area to the left, it's going to give me this. I know how to find the area to the right by subtracting from 1. So again, we're going to look for 2.16. So coming back to the z table, 2.16, we go to the 2.1 row, and we're going under the 0.06 column. And that looks like this entry right here is 0.9846. So this area right here that's not shaded is 0.9846, which means the area of the region we want is 1 minus 0.9846, which is 0.0154. So a very small probability. And there we have that. So that's how we find probabilities using the standard normal curve. Okay? I could add another one in here. I think I will actually. So let's say we want the probability that z is between negative 1.12 and 2.16. So in looking at that, so I'm going to draw my normal curve, just like normal. And no pun intended there. So 2.16 is here, negative 1.12 is here, and I want this area. Now this looks a little bit different than what we've done before. But if you think about it in steps, try to think of it in terms of what the table is giving us. We know that the area to the left of 2.16 is something. So if I look up 2.16, I get some area. And if I look up negative 1.12, I get some area. And then we have to do something with those areas. Well, let's think about this. If I look up the area to the left of 2.16, I'm getting too much. And so I'm going to have to subtract something off. If I look up the area to the left of negative 1.12, that gives me exactly the amount that I didn't want. So we're going to look them both up, and then we're going to subtract the bigger area minus the smaller area. So 2.16 looks like, oh, we just used that. That was 0.9846. How convenient was that? And then the area for negative 1.12, we go to the negative area, or the negative z-score portion. Negative 1.12 is over here at 0.1314. And if we subtract those, we get 0.8532. And that is our probability. Okay? So now let's look at an application, and here is where we're going to really see the correspondence. So you notice I drew a lot of things here. So if I want to use any mu and sigma, so let's say the time to transfer, clean, and partition a file is normally distributed with a mean of 1.5 hours and a standard deviation of a quarter hour, which is really 15 minutes, but units are very important to make sure we line them up. So we have to use the same units for each piece. So this right here is what the distribution for x looks like, where x could be any standard normal random variable. And we know already that if I tick off by the standard deviations here, so my mean here is 1.5, one standard deviation above is 1.75, one standard deviation below is 1.25, and so on and so on. Those values of x correspond to these values of z. So if I happen to land on one of those values of x that's special, we can answer this question more easily. Just as an example, if I'm with the probability that x is greater than or equal to 1.25, this is the same as saying the probability that z, the standard normal random variable, is greater than or equal to negative 1. Now once again, we can look at our standard normal chart for this. So if this is negative 1, we want this area. So remember what happens when you want a greater than. We look up the area to the left of negative 1, and then we subtract from 1. So if I look for negative 1.00, that should be right here, 0.1587. So that means the area that we want is 0.8413. So that's our answer. So if you're trying to get out of there in under an hour and 15 minutes, you're out of luck. You have an 84% chance of it taking longer than that. Now let's try to find the probability involving a different value. Let's say it's one that's not a whole number of standard deviations. Let's say 1.4. So that means that we're right about here. So the question is, what is the z-score, which again means what is the number of standard deviations from the mean this is. We might remember a formula that relates the z-score to an x-score, and that was x minus mu over sigma. So the first thing that we do is convert 1.4 to its corresponding z-score. And that looks like negative 0.4. So finding the probability that x is less than or equal to 1.4 is the same as finding the probability that z is less than or equal to negative 0.4. And that again we can get from the chart. So negative 0.40 is all the way over here, so 0.3446. So we want to know the chance that a randomly selected file is going to take 1.4 hours or longer to process. This is our probability, which means it's quite likely. So that is using the standard normal distribution in conjunction with any general normal distribution. I hope you found this video helpful, and thank you for watching.